So this time what we're going to do is we're going to find values of a and b such that this piecewise defined function is defined for the entire real number line. So basically what they're saying is they have this theorem that they usually give you in the class or in the textbook, which will say that these standard types of functions are continuous on their domain. So linear functions and polynomials and reciprocal functions and algebraic functions for the most part and trigonometric functions, and all of these functions are continuous on their domains, that says. So what they're saying is if I have a constant function or a linear function, it will be continuous everywhere on its domain. So in these intervals where they split it up, it definitely will be continuous everywhere. What you have to do in these types of problems, and what they mean is they've given us two switch points. They've broken up my function into three functions, which means it had to switch in two spots, at 0 and at 1. So what I'm going to do with that information is look at the left-hand limits when I approach that problem point, and look at the left hand and right hand limits when I approach the other problem point, and get two equations. This one looks like, because I have such constant and such simple functions, it's probably going to be fairly easy equations, and that's what we want to do at first, see what the idea is and not make the functions too complicated. So the functions aren't complicated, they probably will get much more complicated, but right now this is what I'm looking for. To find these two things uniquely somewhere, I have to have two equations and two unknowns. This is essentially linear algebra, so watch some of those videos. In the more complicated ones, you'll see I row reduce a matrix to find the unique solutions because it's faster. What am I going to do with this? I want to compute at x equals 0 as a trouble point. So from x equals 0, what we're going to do is compute the left-hand limit. The left-hand limit is equal to the limit as x approaches 0 from below of f of x. And then you say, well, which one do I use? Well, when x is less than 0, I use this function. So this is equal to the limit as x approaches 0 from below of -1, which is -1. And now I compute the right-hand limit at 0. The right-hand limit is equal to the limit as x approaches 0 from above of f of x. And then what do I use? Well, I use this function because when x is larger than 0 but near 0, it is ax plus b. So that is the limit as x approaches 0 from above of ax plus b, which is a polynomial which I can put in there, which just gives me b. Now this is why this one's not so bad. What that tells me now is for it to be continuous at 0, I need the left-hand limit to equal the right-hand limit. The only way that's going to happen is if these two things are equal to each other, and that gives me immediately b is -1. So now we know what b is. b is -1. This actually, we can probably put that in there. Let's try and make that simple for us because this one's going to be easy. That might be a non-standard move for you at first, but I know what b is. It's -1 for that to work at 0. Now I have to have, for continuity at 1, I want the limit as x approaches the left-hand limit will be at 1, will be as x approaches 1 from below of f of x, which is equal to the limit as x approaches 1 from below of, again, when I'm near 1 but below 1, I'm still this function, but now I'm ax minus 1 because I know what b is. And that equals a minus 1. Again, I evaluate where am I going, 1 from below. Can I put that in there? Yes, I put it in there and it doesn't cause a problem, and I get this. So that's the left-hand limit. The right-hand limit, the limit as x approaches 1 from above of f of x is equal to the limit as x approaches 1 from above of, now what do I use? When I'm above 1 but near 1, I'm 2. So I get that this equals 2. So the only way we're going to have this is if this left-hand limit again equals the right-hand limit, so a minus 1 equals 2 or a equals 3. So basically, once we have that, you can actually explicitly do that and then draw the function if you want, but what are we going to get? We are going to get 3x minus 1 is the function which is continuous on the entire real number line.
Can we do another one of these?
Yes. This time what we're going to do is step it up a little bit. We're going to play the same game, which is probably horrible if you've been asked already. We're mixing different subjects even to be clever, linear algebra a little bit, which is going to be what happens. So hold on. I know, linear algebra, everyone hates it, even the cat. So what we're going to do is find a and b such that this function is continuous on the real number line. Now it's much more complicated. We've got a linear function and a quadratic and another linear function. And so it's split again at 2 points. And to make this continuous everywhere and to find a and b, what we're going to have to do is find the left-hand limit and the right-hand limit at -1 and at 1, and then get 2 equations and solve for those. So basically, for x equals -1, we have the left-hand limit is the limit as x approaches -1 from below of f of x is ax minus b, which is going to equal -a minus b. And then the limit as x approaches -1 from above of x squared plus 2a plus b is going to equal 1 plus 2 times plus 2a. The 1 only goes, x is going to -1, not a. 2a plus b. Now I want to set those two things equal to each other so that the limit will exist and that the left-hand limit will equal the right-hand limit. Those were words. So what does that say? These two things are equal. -a minus b equals 1 plus 2a plus b. So that says, I'm going to bring this over and this over. That says 3a plus 2b equals -1. That's my first equation. So I have one equation involving a and b. I don't have enough information, and this is what confused everyone. They want to just keep going and have a linear line, pun intended, I guess. They want to have a linear line to getting a and b. But now what we have to do is stop and take a break and put that one down for a minute and go back to now at 1 and find another equation that involves a and b. And then we'll have 2 equations and 2 unknowns, and we're going to augment a matrix and do the whole thing. So now let's look at 1. That's how you change that. Now at x equals 1, what we're going to do is the limit as x approaches 1 from below of f of x is x squared plus 2a plus b again, which is equal to 1 plus 2a plus b. It was squared, so it's going to be the same value at 1 and -1. The limit as x approaches 1 from above is going to be 3x minus 7, which is going to equal 3 minus 7, which is -4. So for these two things to be equal to each other, that says that 1 plus 2a plus b has to equal -4, or that says 2a plus b equals -5. That's what we get from that system. So let's recap for a second. Given this function, we wanted to find a and b where we get continuity everywhere. So the two possible troubles are at -1 at 1. We found the left-hand limit and the right-hand limit at -1, and we got this equation. We found the left-hand limit and the right-hand limit at +1, and we got this equation in a and b. Now we're going to switch into linear algebra mode. So if you don't know, in slightly other videos, or the strategy is in this one, you could solve for b. b is -5 minus 2a. And then you can plug that into here, and then you can solve for b and a that way, back substitution. But I'm going to do it a slightly different way using augmented matrix and row reduction. So from this system now, what that says is I have a linear system. 3a plus 2b equals -1, and 2a plus b equals -5. I immediately, if you know what you're doing, I get an augmented matrix. 3, 2, -1, 2, 1, -5. I don't like dividing by fractions or dividing by integers to get leading ones to get fractions. Instead, I see that 3 minus 2 is a leading one. So I'm going to do the rare thing where I change row 1 to get a leading one. Row 1 goes to row 1 minus row 2. And I get 2, 1, -5. I didn't change row 2, so I'm not going to alter it. Now I'm going to do 3 minus 1 is, or 3 minus 2 is 1. 2 minus 1 is 1. And -1 minus 5 is 4. Now that I do that, I have a leading 1. I want to get rid of this. So I'm going to go to row 2 goes to row 2 minus 2, row 1. So we're multiplying by -2 and distributing into every spot and then adding it to this. That will give me 1, 1, 4. 2 minus 2 is 0. 1 minus 2 is -1. And 5 minus 8 is -13. trying to get me. I made the question up myself, trying to get myself. Apparently. I'm lazy, but we're going to multiply this row by negative 1. I guess I'll do it. Row 2 goes to negative row 2, and it gives me 1, 1, 4, 0, 1, 13. That's still not too bad. What does that say? I'm now in row echelon form, and that tells me that 1 times b is equal to 13, or b is 13. And then what does this equation tell me? That says a plus b equals 4, or a is 4 minus b, which is 4 minus 13, which is negative 9. So the unique solution to this, the a and the b that will work to make this function continuous everywhere are b is 13 and a is negative 9. What was the original function? The original function was f of x equals a plus negative b. So negative 9x minus 13 if x is less than or equal to negative 1. And then it was x squared plus 2 times a, so minus 18x plus b plus 13 if negative 1 is less than x is less than 1, and we are the function 3x minus 7 if x is greater than or equal to 1. This was the function, the unique two values which created. So now that we calculated those values, we got a was negative 9 and b was 13. They can actually go into this function, and this is the unique function which is continuous on the entire real number line for a and b values.